Bismillahirrahmanirrahim. This is a course of inorganic chemistry, and today we'll talk about the classification of crystals on the basis of bonding. This lecture will include the topics: what is a bond, what is a molecule, and what is a crystal, and classification of the crystals, non-molecular crystals, ionic crystal. The non-molecular crystals include ionic crystals, covalent crystals, metallic crystals, and the molecular crystals. So, what is a bond? Isolated atomic species can come together to lower the overall energy of a system. This is why bonds are formed, because when the atoms combine together, they make a new system of lower energy. The molecule is of lower energy than the isolated atoms. The combined states where the atomic species exist together is called bonded state. The interaction between any of the constituent atomic species can be referred to as bond. The bond may be formed formed between a limited set of atomic species to form a molecule, for example, water, methane, etc. Or the bond may give rise to an extended solid like copper crystal or the silicate glass. The silicate glasses are not considered as the ground state of solid. Electronic interaction between atoms may lead to the lowering of energy of the system as compared to a state wherein the atoms are far apart. The interaction involves the charge and spin of electron. The charge redistribution occurs on the formation of bonded state. Bonding is an easily accessible term for electromagnetic structure of an assemblage of atoms, molecules, or ions. The interaction between atoms, molecules, or ion may lead to lowering of the energy of the system, the bonded state. The interaction between the atomic species could be strong or weak. The strong bonding interaction are covalent or ionic, second, and the third is metallic. Sometimes the metallic bond is considered as a special case of combination of the other two types. That is, the weak interaction include the hydrogen and the van der Waals bonds. What is a molecule? In molecular solids, the bonding responsible for the formation of a molecule, for example, water, is of covalent nature. However, weak interactions are responsible for the formation of an extended solid like the ice crystals. The liquid state can also be considered as a bond state as there is some interaction between the species involved, for example, mercury and water. There are some type of weak interactions involved in converting the gas to the liquid, which has led to the formation of a liquid, else everything would be in the non-interacting gas state. In many solids, the bonding may have a mixed characters. For example, the bonding in zinc sulfide has both ionic and covalent character. We have already noted that the bonding in ice has contribution from both covalent bond, that is between the oxygen and the hydrogen, and the hydrogen bonding between the water molecules. The concept of a molecule is most suited for covalently bonded or with a polar covalent bond species like water, methane, ammonia, and C16. For crystalline solids like copper crystal, sodium chloride crystals, diamond crystal, the concept is practically useless as the entire solid has to be considered as a molecule. In molecular crystals like water, we may still want to retain the concept of water molecule with weak interactions with the other molecules. Now, what is a crystal? Atoms bond during chemical reaction to result in a crystal formation. Crystals are defined as a solid state of matter in which the atoms are packed together tightly. Crystalline solids are well ordered, have definite arrangement of molecules, atoms, or ions. This is the crystal of a diamond. You can see that inside the diamond, all the carbon atoms are arranged in specific pattern, that is the tetrahedra, and the tetrahedra are further connected with each other through a specific bonding, specific arrangement. Now, classification of the crystal. There are two types of crystal can be identified on the basis of the bonding, the molecular and the non-molecular. The crystals molecular crystal and the non-molecular crystal. The molecular crystals, molecule held together by primary covalent bonds. Intermolecular bonding is van der Waals, hydrogen bonding, or other weak type of interaction. That is, in the molecular crystal, we can see the weak bonding interaction. While in the non-molecular crystals, we can see the covalent bonding, ionic bonding, or metallic bonding. The real crystals have bonding characteristic lying somewhere in this triangle. This is a triangle. We have ionic, covalent, and metallic bonding character at the three corners of the triangle. So the bonding can be somewhere in between this triangle. It means that it's possible that the bonding is the mixture of ionic and covalent, or covalent and metallic, or ionic and metallic, but all the bonding interaction will be somewhere here. The metallic bond is very different from the ionic and covalent bond. This implies that the molecules are good conductors, no band gap, while non-metals have a band gap and are insulator at 0 Kelvin. Now the bonds. The bonds can be metallic or non-metallic. In the metallic ion core in a sea of electron, you know the concept of the free electron. Non-metallic bonding can be of covalent or ionic type. In covalent, there is equal share of electron between the nuclei, and in ionic bonding, there is an unequal sharing of electron. In metallic crystal, the bonding electron density is uniform throughout the crystal. This is the case of the first one, metallic crystal. In covalent crystals, the electron density is high between the nuclei, while in ionic bonding, the electron density is higher around one end of the nuclei. So the bonds can be either non-directional or directional. In case of metallic and covalent bonding, the bonding is non-directional, while in case of ionic, it is directional because the electron density is towards the one end. Now, ionic crystals. When ionic crystals are formed, electrons jump their orbits to bond with the corresponding supporting atom. The resultant combination of the negatively or positively charged electrostatic forces stabilizes the ions. It is clear from the name. These are the ionic reactors, so they will be formed of the positively and negatively charged ions. According to Coulomb's law, the attractive forces found between the atom pull the atom together, and this action is inversely replicated because of the similar charges between the same ions. Example of the ionic crystals. There is the ionic crystal results in a very strong bond of atom in the crystal. These highly intense forces attribute high melting and boiling points and rigid structure to these crystals. Examples are the ionic crystal of sodium chloride and zinc sulfide. So the picture is showing the ionic crystal of sodium chloride. The properties of the ionic crystals. You can see here in this picture that the ionic crystal is formed of negatively and positively charged ion throughout the structure. In this picture you can see the example of the sodium chloride, in which the sodium ion and the chloride are attached with each other through electrostatic interaction. The ionic crystals are hard and brittle. They are having high melting points, high heat of fusion, good electrical conductors, and thermally stable. They are electrical conductors in a solution form. In solid form, they are non-conductor, but in solution form, they are good electrical conductor. Covalent crystal. A covalent bond is a crystal structure in which the electrons do not leave their orbits. Electrons instead are shared between two atoms. A shared electron in this way bonds every two adjacent atoms. The bound atom further share another electron from the atom next to them, and so on. Covalent bonding between the atoms of a substance result in the formation of geometrical crystals. These are examples of the covalent crystals. Diamond, and you can see the structure of the tetrahedral structure of the carbon atom, and that carbon atoms are arranged in tetrahedra. And this is a graphite. You can see that the carbon atoms are arranged in hexagonal rings, and these hexagonal rings are making sheets. The sheets are connected with each other through the van der Waals forces. The ionic crystals are very hard. You know about the diamond, it is the hardest material, very high melting points, poor thermal and bad electrical conductors, except graphite. Graphite can conduct. And examples of these are diamond and quartz and silicon. Now the third type is the metallic crystals. In these type of solids, the constituent particles are metal atoms. The interparticle forces in these solids are metallic bonds. In the metallic crystals, the metal atoms occupy a fixed position, but their valence electrons are mobile. In the closed-pack assembly of the metal kernels are the part of the metal atom without valence electron, remains immersed in the sea of mobile valence electrons. The attractive force between the kernels and the mobile valence electron is termed as metallic bond. You are well aware of the concept of the metallic bond. In the metallic bond, we have a sea of free electron. The valence electron of each atom are free from the nuclei, so they are making a sea of free electron, and the sea of the electron ejecting is negative ions, while the positive part of the atom, the kernel, ejecting is negative ions. So there is electrostatic of forces of attraction between this the positively charged part of the atom and the negative electrons. The metallic crystals are fairly soft, low to moderately high melting points, and poor thermal and electrical conductors. Uh, this is a mistake. They are not poor electrical conductors. Rather, they are good conductors because they have free electron in their structure. These are soft, so they can be shaped into they can be shaped into different forms. The molecular crystals are solids that consist of atoms or molecules held together by van der Waals forces, length dispersion, dipole forces, and hydrogen bonding. So the van der Waals forces are of three types: London dispersion, dipole forces, and hydrogen bonding. The molecule can be polar or nonpolar. These crystals are fairly soft, low to moderately high melting points, poor thermal and electrical conductors. Examples are dry ice, which is a solid carbon dioxide, and solid methane. You can see here example of solid carbon dioxide uh, forming solid materials, solid pellets, and this is the methane, which are in the solid phase, and also the iodine. The van der Waals bonds in crystal. A van der Waals bond is a weak interaction between the atoms of the substance, resulting in soft constituency of the crystals. The outer orbit of the atom is completely filled with sheer electron, but their charges keep transferring. Many organic molecules form crystals where the molecules are bound by van der Waals forces. In methane, a central carbon makes a covalent bond with the hydrogen, forming a tetrahedron. And then the tetrahedron are attached with each other by van der Waals forces. So hydrogen bonding in the crystal. A hydrogen bond is formed when an atom of a hydrogen is attracted towards the respective electrons of the corresponding atom. This interferes with the crystal formation. A hydrogen atom, after being bound to another atom, is pulled towards the negative charges of the neighboring molecule. This confines the hydrogen atom between two negative charges. Hydrogen bonds are commonly found in ice crystals, where the hydrogen atoms are packed tightly between two oxygen atoms. Now, the properties of all the type of crystals are summarized here in a table. So, if we have the atomic particle can have London dispersion forces of attraction between them. So they are soft, very low melting point, poor thermal electrical conductors. Example are the noble gases. The molecular crystals can be polar or non-polar, and they have van der Waals forces, that is the London dispersion, dipole forces, and the hydrogen bonds. They are fairly soft, low to moderately high melting points, and poor thermal and electrical conductors. Examples are the dry ice and the solid methane. The ionic crystals are formed of positive and negative ions, and they have the ionic bond, and they are hard, brittle, high melting and boiling points, and high heat of fusion, and poor thermal and electrical conductors. They can conduct in the solution form. Examples are sodium chloride and zinc sulfide. Covalent crystal, the atoms that are connected in covalent bond network, they are very hot, very high melting points, poor thermal and electrical conductors. Examples are diamond, quartz, and silicon. In this case, the only conductor is the graphite. And then we have the metallic crystals, cations in an electron cloud. They are connected by metallic bonds. They are fairly soft, low to very high melting points. They are excellent thermal and electrical conductors, and they are malleable and ductile. Examples are all metallic elements, for example, copper, iron, and zinc. This is a link you can practice practice more about the classification of crystals. You may open this link, you can find very useful information relevant to this topic. This is the structure of the crystalline quartz. You can see that the tetrahedra are arranged with each other in a regular pattern. The tetrahedra are composed of the silicon and the oxygen. The letters of the crystalline quartz, the atoms form a regular arrangement structure that consists of length tetrahedra. Now I have put some questions, test questions for you. You have to take the question, read it, and think over it, think the possible answer. In the next slide, I have given the answer. Then you can check with the answer what you have already thought. How do amorphous solids differ from the crystalline solids in each characteristic? Which of the two types of solid is not similar to the liquid? Think over it for a minute and write the answer in your mind, and then you can cross check with what I have given. The answer, the rigidity of the structure, long range order and short range order. Which of the two characteristics the amorphous solids differ from the crystalline solid? Why is the arrangement of the constituent atom or molecule more important in determining the properties of solid than a liquid? The arrangement of atoms or molecule is most important in determining the properties of a solid because of greater persistent long-range order of the solids. Gases and liquids cannot readily be described by the spatial arrangement of their components because rapid molecular motion and rearrangement defines many of the properties of a liquid and the gases. Another question. A student obtained a solid product in a laboratory during the synthesis. To verify the identity of the solid, she measured its melting point and found that the material melted over a 12 degrees centigrade range. The range is quite long. After it had cooled, she measured the melting point of the same sample again and found that this time the solid has sharp melting and a sharp melting point at the temperature that is the characteristic of the described product. Why were the two melting points different? What was responsible for the change in the melting point? Think over it for a minute and then go to the answer. The initial solid contained the described compound in an amorphous state, as indicated by the wide temperature range over which the melting point occurred. She cooled the liquid. When she cooled the liquid, caused it to crystallize, as evidenced by the sharp second melting point observed at the expected temperature. From this experiment, it is clear that if you have the solid in amorphous form, you can have a long, wide range of temperature. But if the compound is in crystalline form, you will have a sharp melting point. Now, another topic is included in the same lecture, that is the non-stoichiometric compounds. Non-stoichiometric compounds N is a solid chemical compound in which the number of atoms of the element present cannot be expressed is a ratio of small whole number. Whole numbers are like if we have 1 to 1 ratio of the two elements, or we can have more than two elements in a single compound, but the ratio is in whole number. Whole numbers are 1, 2, 3, 4 up to the 10, and integers are, but we cannot represent these compounds in a whole number. Another definition is an elemental composition cannot be represented by a ratio of well-defined natural numbers and therefore violate the law of definite proportion. Solid follow the law of definite proportion means that the components are in ratio of whole numbers. But in non-stoichiometric compounds, the ratio of the atoms in a compound or in a molecule are not in whole numbers. These compounds are sometimes called as Berthollet compound in distinction from the deltonides compound in which the atomic ratios are those of small integers. Non-stoichiometric compounds are best known among the transition elements. Several of them are important. Important is component of solid state electronic devices such as rectifiers, thermoelectric generators, photodetectors, thermistors, and magnets useful in the frequency circuits. So the non-stoichiometric compounds have many uses in this area. How non-stoichiometric compounds are formed. The existence of the non-stoichiometric compound is related to the presence of defects in the lattice structure of the crystalline substances, such as the absence of ions from a site that would be normally occupied. For example, if we have a crystal structure, we have the atoms or the elements in a proper ratio of the whole numbers. But if it's some points are replaced by impurities or some other elements, the normal ratio will be disturbed. So the compound will not be in the compound. The ions or the atoms will not be in the whole number ratio. Since the solids are overall electrically neutral, the defects in the ionic compound is compensated by a change in the charge of other atoms in the solid, either by changing their oxidation state or by replacing them with atoms of different elements with different charge. So, since the solid, if the we have talked in the crystal defects, that it is just possible that the impurity which is coming from the outside may have the same charge as the particles of the crystal have. So then in that case the total charge on the crystal will not be disturbed. But if the impurity is having different charge, the total charge on the crystal will be disturbed. But in order to maintain electrical neutrality, they will have to get some type of ions from the outside, which lead to the formation of the non-stoichiometric compounds. Example of the sodium chloride. For example, a sodium chloride crystal that lacks a sodium ion and a chloride ion is defective, but still stoichiometric because the number of the sodium ions and the chloride ions are the same. If the sodium ion site, however, is filled by neutral sodium atom, which then gives up its valence electron to fill the chloride ion site, the crystal defect is remedied. But the crystal is now non-stoichiometric because it contains more sodium ions than the chloride ions. Means that if the sodium ions are replaced by neutral sodium atom, it will lead to the synthesis of non-stoichiometric sodium chloride crystal. Example of ferrous oxide. Non-stoichiometry is uh, pervasive for transition metal oxides, especially when metal is not in its highest oxidation state. For example, although ferrous oxide has an ideal formula FeO, the actual stoichiometry is closer to FeO or not exactly in 1 to 1 ratio, but that is like 0.95 percent of the iron in 100% of the 1% of the oxygen. They're in the ratio of 1 to 0.95. So this is a non-stoichiometric formula. The non-stoichiometry occurs because of the ease of oxidation of iron to change from +2 to +3, effectively replacing a small portion of the Fe plus 2 with two-thirds their number of Fe plus 3. That the iron plus 3 state can easily replace the iron in plus 2 state. Thus, for every 3 missing iron in plus 2 state, the crystal contain 2 ions with N plus 3 state to balance the charge. If we have these 3 particles for iron with plus 2 charge, we can have the oxidation state of 6. So they will be replaced by 2 particles of iron with plus 3 charge, where the oxidation state is plus 3. This will lead to the non-stoichiometric ratio of the iron and oxygen. The composition of the non-stoichiometric compound usually varies in continuous manner over a narrow range. Thus, the formula for this iron oxide can be 1 minus x, where x is a small number, varying from 0.05 in the previous example, representing the deviation from the ideal formula. The ideal formula is that they are in the ratio of 1 to 1, but actually they are not in the ratio of 1 to 1. In these compounds, there are specific ways to account for the missing or the extra atoms. A variable is added to coefficients to show that the compound is not in a entirely stoichiometric ratio. Like here we have added a variable x, which shows that the compound is not in the ratio of whole number, but it deviates by a small value. If the metal or non-metal ratio is greater than the stoichiometric, then there is either excess metal or missing non-metal. This is a metal in this case, and this is a non-metal. If the ratio of the metal is greater than the non-metal, so either the metal is in excess amount or the non-metal is and the non-metal and the non-metal few atoms are missing. If there is a missing non-metal, it is represented as, for example, and we have this molybdenum and oxygen, we write it as 3 minus 6. But if the metal is in excess, we can write it like 1 plus x, and then we have the oxygen. If the metal non-metal ratio is less than the stoichiometric, then the situation is possible. The missing metal is represented by the compound, like we have rhodium, we write it as 1 minus x, and then the oxygen. The normal formula will be that they both will be in 1 to 1 ratio, but here we write this variable to show the non-stoichiometry, and extra nonmetal is represented by the compound, like we have W and the tungsten and oxygen, and the oxygen and the tungsten would be in normal case they will be in the 1 to 2 ratio, but in the non-stoichiometric compound they are written as like there is a 1 for tungsten, and the oxygen we write an extra variable x. If another element replaces the missing atom called impurity material, it is the best to consider it is S is a simple solid solution. Like we have the metal and it is replaced by either the normal metal is replaced by some type of impurity, or there is a vacancy, or in any extra atom comes here. This is the situation which we already talked about the previous lecture of the crystal defects. All these situations can lead to the synthesis of non-stoichiometric compound, as the normal ratio is disturbed in all these cases. There are applications of the non-stoichiometric compounds. Many non-stoichiometric compounds are important in solid state chemistry and have application in ceramics and superconductors. For example, yttrium barium copper oxide, the most notable high-temperature superconductor, is a non-stoichiometric solid with formula represented by this. In this, we represent the ratio of the yttrium by x, barium are 2 atoms, and copper are 3, and the oxygen is also variable. We represent it by 7 minus x. So this is a non-stoichiometric compound, and it is having a use as a superconductor. You all people are well known with the importance of the superconductors. The critical temperature of the superconductor depends on the exact value of X. That is we can see that X here and here. The stoichiometric species has X is equal to 0, but this value can be as great as 1. Thank you.